Hi everyone. So this video is an introduction to stochastic gradient descent. Basically, we've been talking about it until this point, all along until this point, but it's worth explicitly introducing it for concreteness in order to discuss its aspects later. So gradient descent, because basically we are following the direction of the negative gradient. So we compute the gradient of the cost function with respect to the parameters. We follow the negative direction so that we minimize the cost, right? And stochastic, traditionally the word stochastic was used to mean update every single example. But now it's more common to use it even with many batches of many examples. But it's still the case that these many batches contain very few examples with respect, with respect to the size of the whole training set. So stochastic comes from the fact that I use a small set of examples to compute the gradient and compute my parameter update. So after a many batch is sampled, and as we said, sampled, ideally you want to sample it randomly from the training set. But what happens with very large data sets is that you shuffle the data set and you store it in the shuffled order. You shuffle it once and you store it in the shuffled order, and then you basically take in a deterministic way from the shuffled order, exactly like you do with a deck of cards, right? So you sample the mini batch, or you select the next mini batch from the stored shuffled training set, and then you compute the gradient. So let's say the mini batch has m examples, then the average is simply 1 over m. You divide by 1 over m, and you compute the gradient with respect to the parameters, theta, right? So theta here, these are the parameters, and basically you sum the loss over all the examples. So let's say I is the index of the examples, and this is the loss function L of f of x of I and theta. F is basically the function that computes the value of the output units given the ith example as input, and theta the current setting of the parameters, and yi the given training labels, right? So the loss is a function of the computed output units and the given training labels corresponding to the ith example. And it's important here that we are using theta, the current setting of the parameters, to compute the loss, to compute the gradient, right? And then we update the parameters, right? And as we'll see later, there are variants of stochastic gradient descent where that order is not necessarily done in this way, right? So here I compute the gradient based on the old parameter setting, and then I update the parameters. And I update the parameters basically by subtracting the current gradient multiplying by the learning rate. And epsilon k is the learning rate in the kth step. It doesn't have to be that epsilon k is the same for all k, so I could change, as we mentioned in the last video, we could have an adaptive learning rate. So we could change the learning rate from one training iteration to another. Now in the video after next, all of it will be about the convergence guarantees of stochastic gradient descent, but just a basic result that we will discuss here. We will not discuss the proof, but we will give a rough idea behind it, right? So SGD is guaranteed to converge if you have these following two conditions. Basically, the sum of the learning rates is equal infinity, right? So meaning that the learning rate doesn't vanish very quickly, right? Such that it becomes zero, right? So the sum equal infinity, meaning that I always keep, as I go on in further training iterations, I always keep a positive learning rate, right? But the sum of the square has to be finite of the learning rate. So the learning rate has to drop, right? I cannot have a constant learning rate. If I have a constant learning rate, I don't have a guarantee on convergence. To have a guarantee on convergence, the learning rate has to vanish, right? But it has to vanish not very quickly, right? So it has to vanish. The square, the sum of the square, it has to be what's called square summable, right? The sum of the square is finite, but it's not absolutely summable. the sum of the elements themselves are infinite, right? So what's the intuition behind this condition? Is basically what we said before when we analyzed the second order Taylor series of the cost function, right? We said, so remember in the video where we discussed the L conditioning of the Hessian, we said that every parameter update adds half epsilon k square and then GTHG, a second order term, H is the Hessian, minus epsilon k GTG. Right? So you want this second term to dominate, right? So meaning the learning rate itself has to remain significant, but the square of the learning rate has to vanish, right? So the intuition is that if you have this condition, then epsilon k square will be very small, so that you will not add new terms to the cost, but rather you would subtract terms from the cost, and that's why the cost becomes minimized and SGD has a convergence guarantee whenever these two conditions exist. Thank you.